Okay.
Hello, hi everyone. Thank you for joining the Geoscience and Geoenergy webinar of today, 4th of November 2021. Today, Sebastian and myself have the pleasure and honor to host you all and our distinguished speaker, Professor Matteo Lupi from the University of Geneva in Switzerland. Matteo obtained his Master of Science in Earth Sciences from the University of Pisa in Italy in 2005. Then he worked in the private sector developing groundwater flow models of swamp regions. Then later in 2006, he moved to the Institute of Petroleum Engineering at Heriot-Watt University, and not that far from Sebastian's office, I would say. So he was his first PhD student who still remembers good memories about the time he had with Sebastian, by the way. And then at Heriot-Watt, he did his PhD in which he investigated large-scale fluid flow and fluid-driven seismicity in the upper crust. He obtained his PhD in 2010 and then moved to Bonn in Germany to study the Lucy-Maud eruption in East Java. After 2 years in Bonn, he was then funded by ETH Fellows Scholarship for 2 years. So he goes to Zurich after Bonn in Germany, and next he was also awarded with the SNF Ambizione grant to investigate fault reactivation in oblique subduction zones. In 2015, then he finally arrives where he is now. He becomes assistant professor, a tenure track assistant professor, and then just recently this year in July, he was promoted to associate professor. He has built a group on crustal deformation and fluid flow at the University of Geneva, where he works today. It's our pleasure and honor, Matteo, to host you today. Thank you for graciously accepting our invitation. To the audience, please note Matteo's lecture would last for about half an hour, followed by questions and discussions. Like always, please do type your questions in the chat box. And Sebastian will, like always, go through them and share the discussion session. Do not wait until the end of the talk to post your questions. Whenever appropriate, please do type them. Your question can trigger other questions as well. So without any further ado, Matteo, the stage is all yours, and thanks very much once more for this lecture. We are very much looking forward to hearing your talk.
Thank you very much, Hadi. Thank you very much, Sebastian, for inviting me and be part of these webinars at the Geoscience and Geoenergy community. Thank you also very much for the introduction. My name is indeed Matteo Lupi, and I decided to post this very Swiss kind of image to show that renewable energies are indeed possible to be deployed also in places that are logistically not so easy to reach. So this is the typical pictures of a Swiss mountain hut, and you could see standing there a nice solar panel that feeds the hut with some electricity. So I decided to start with something that we all very much know, the work of Mann and Bradley. And this is just to kick off some discussion how we should actually meet the energetic goals that were established during the Paris Agreement. Just to remind once again, unless these timelines are not modified in these coming days in Glasgow, in 8 years, we will have to reduce by 45% our CO2 emissions, and by 2028 year only, our renewable energy supplies will have to be up to 80% of power by 2050. 28 years only. It is going to be challenging, but let's see how do we arrive from the Paris Agreement to the group of crustal deformation of fluid flow at the University of Geneva, and what is the procedure that has been followed, and how this vision has been distributed top down. So we have an international panel of experts on climate change that decide to follow some guidelines. Then for what concerns each country, these guidelines are distributed to each country, in this case in Switzerland at the Federal Office of the Energy, that leads the formation of an Energy Act that was actually voted on in May 2017. Following this Energy Act, there are several competence centers. The one I belonged to is called SSER, and is a competence center that goes across university and industry with the method of developing innovative and sustainable solutions for reducing, for fighting climate change, and to meet the energy strategy by 2050. As part of these competence centers, various universities and various industry are part of it, and University of Geneva, where I'm hosted, is also part of it. So within the University of Geneva, there is my group of research, there is a group of research of other colleagues, and there are several groups that are working in parallel on different topics to carry on research towards a mitigation of climate change. And finally, we actually develop on a research on a specific case, and in this case, today we will discuss about geothermal energy. This is nowadays an old picture from a mountain hut in the Swiss mountains, and this is the group of crustal deformation of fluid flow now 2 years ago. So when we discuss about and we think about geothermal energy, we think about steaming environments when there is the magma nearby the subsurface, and when there is a lot of resources easily accessible. Today we will discuss instead about sedimentary basin, more specifically the western side of Switzerland, the Great Geneva Basin, when the geothermal gradient is not so high, but nevertheless we would look for geothermal resources by looking at the heat in the subsurface, the fluids that are the vectors, so the mean by which we transport heat and energy, and seismicity. Seismicity, you may have heard that seismicity is, of course, has to be hindered, and we have to start to face the risk of seismicity associated with geothermal energy. This is because geothermal energy is very often reported by the media as a large system. So there's no specification about shallow geothermal systems, heat exchangers, or enhanced geothermal system. Geothermal energy is equal to seismicity. We know that this is not always the case because different geothermal systems imply a different rate of seismicity, but nevertheless, seismicity is the place that we have, the location of seismicity is something that we have to look at because is also pointing out towards deformation. And deformation means permeability, and permeability means sustained fluid flow in the subsurface. So by combining all these aspects, we would be able to try to find out towards the end of this talk about geothermal energy in Switzerland. So we will discuss about this part of Europe. More precisely, this is the Lake Léman. This is the city of Geneva. Zurich is somewhere here. Berlin is far north there. And we are located, geologically speaking, in a foreland basin that is enclave between the Alpine front in the south and the Jura Mountains in the north and towards the north. This is a foreland basin, and if we go and see a cross section striking from northwest to southeast, we do see the general geodynamic setting where we have thrust faults and fold and thrust, and a typical fold and thrust belt. We will investigate this region here where there are different type of fault systems spanning from northeast or let's say subparallel alpine thrust faults and strike slip fault system striking more or less northwest to southeast. There has been a large campaign to investigate the fault systems of this region, and we do have, as I said, also the small-scale thrust faults and strike slip fault system. In the area has been evaluated for the geothermal potential for different units that goes from the Quaternary to the Permo-Carboniferous, which represent the basement, and in between these two units we have a Mesozoic sequence that can be actually exploited for identifying geothermal resources. I think Western Switzerland is a nice example of how the academia and the industry interacted together by launching applied research projects that led to, let's say, industrial relevant type of information. In this case, for Western Switzerland, in Canton of Geneva, we do have an interpolation of different seismic line that would nicely reproduce the subsurface of the Geneva Basin. So with a good understanding of the location of faults, the interaction between the different lithologies and geological discontinuities. The Canton of Geneva is also bringing forward a prospection campaign by drilling progressively 4 wells. In green are the wells that have been already investigated, and the other ones in the south here in purple, in magenta, are the ones that will be investigated in the future. The targets of these wells are progressively deeper and addressing different type of fault settings. So let's have a look at this video. And in this video, we start to enter into a well. And what is quite nice is that outside this well, we see gas steaming. We see hot fluids that are pumped out of this well, and a temperature is not written in the image, but a temperature of about 34 degrees. Actually, this is located in the sedimentary basin of Geneva, and more specifically represents the Satigny well that reached only 700 meters depth, but held temperatures of about 35 degrees at 700 meters depth. And this was a well with artesian pressure. So it was a very productive well with a suggested direct link to the permeable formations, karstified permeable formations that are actually along which fluids are downwelling and then intercepting the fault system in the area. So thermal anomalies in the Geneva Basin do exist and shall be found. In Geneva at the moment, we don't have any particular target for geothermal energy. We would start with shallow depth, and there is a large variety of applications that can be used. Shallow from low enthalpy system to enhanced geothermal system. Well, eventually in the long-term future, geothermal energy could be also harvested from the basement. Today, we will not have time to go through all the research that we have been conducted over the last 5 years over here in the group of the crustal deformation. But just would like to point out that we work at 2 scales. The regional scale that is reported in green, and here we have some examples of the research that's been conducted. This is a scale of the upper crust, so 5 kilometers more or less depth, and 50 kilometers, roughly speaking, on as an aperture of the investigation, and also a bit more higher resolution type of imaging that goes down to 1 kilometer and few kilometers of imaging. So with the green case scenario, we will go a bit more in detail, while for the red case scenario, I can show you some examples. So one of the first things that we started to investigate at the local scale was to develop geoelectrical methods for the prospection of shallow geothermal resources. We decided not to use anymore the classical electrical approach, but rather we invested into this new technology that is called full waver, so which avoids long multi-cord cables and actually allows to deploy independent instruments in the ground that allow not the interpolation of geophysical images, but the full 3D acquisition of geoelectrics. So it's possible to scatter this rather logistically complex hardware in the field and acquire a full 3D image of the subsurface. As you know, I will not go through here about the principle of geoelectrics, as this is just like a small introduction about the method. But when we do a geoelectrical prospection, we are able to investigate both the matrix and the fluids that are hosted into the porous media. And thanks to this, then, is it possible to retrieve images as the one that we follow here. So this is the 2D geoelectrical acquisition that we perform in the well that you have seen in the video before. And what is quite nice to point out is that not only we managed to find below the well a region marked in blue here where there is a marked anomaly, let's say the values of electrical conductivity are rather low, and this nicely correspond to the occurrence of an aquifer, but we do find, heterogeneity, strong resistivity changes, and most importantly, here we are dealing with a seismic line, with a geoelectrical line of about 2 kilometers, and we managed to attain a depth of about 900 meters. Below there is the resolution of this image, and this is just to give you an idea of one of the approaches that we would try to apply here in Geneva. To benchmark this method that so far was only present for, not for the prospection of geothermal resources, but only for the mining sector, in this study, we start to compare the geoelectrical method against the gravity method and the active seismic method, and the results were nicely accepted in GJI. That shows how we could also start to develop new methods for prospection of the upper crust that not necessarily are extremely demanding in terms of economic means and extremely difficult to process. On this type of acquisition, then we can perform some numerical modeling, and this is just another example of what we did by collaborating with colleagues from SINTEF in Norway, where we started to take the information of the first kilometers of the subsurface and started to test whether different sites and different lithologies could be used to store heat and during the summer and recovery during the winter. I'm not going to the detail now in this with this slide, but just would like to point out that it's possible to have an integrated approach with available tools, academic tools. So now let's start a bit to dive into the presentation. The Great Geneva Basin, we have an integrated approach, we say, and our goal is to understand the geological processes. We are academics, so we want to understand the full physics driving fluid flow and geothermal resources in the area, but also we want to have an applied type of approach. So we want to find the best place where to drill. Let's remember a set of coordinates that will come back towards some slide down the presentation. I mentioned before the problem of earthquakes. There is this nice commentary from Domenico Giardini that suggests that earthquake-quake risk must be faced. And this is a project financed by the Swiss Industrial Services of Geneva that allowed us to deploy a seismic network in the region. And when the project was started, there was only one accelerometer in the count of Geneva. For anyone that is acquainted with the seismic method, you will know that it's almost impossible to locate any sort of earthquake with only one station on microseismic activity. So with this project, Veronica, that is a former PhD student of our group, developed in collaboration with colleagues from Zurich and from Geneva, deployed 20 stations around the basin, and this was very important in order to be able to assess the seismic activity of the Geneva Basin before geothermal energy would start. So flipping back between the situation in 2016 and the situation today, you could see that this led also to a major effort for the deployment of more stations that allow us to better characterize the seismic activity taking place in the Geneva Basin. Why this is important? This is important because it allows us to retrieve an accurate velocity model that would then allow us to reconstruct where the seismic activity is taking place, and having this accurate velocity model will be able to would allow us to discriminate whether a seismic event, while for instance there is a well drilling, would have been occurring nearby in the well or further away. So this is the first step in order to understand why it is important to deploy geophysical instruments in the area. But it's also very relevant because this would set a baseline that would witness the degree of seismic activity that is present in a given geological setting before human action would start. In other words, we do know now what is the degree of seismic activity in the Geneva Basin, of microseismic activity in Geneva Basin, before geothermal energy is fully deployed. Not the details that the black dots that you see here in the area are simply the seismic events that have been recorded for 1 year by our network before and after being relocated by Veronica. And in this case, you could see that all the artifacts present in the black dataset are then be readjusted by simply using a better velocity model with the red dataset. This is key because it's important, first of all, to assess whether there is any seismic activity in the basin. And in this case, it's possible to see that there was no seismic activity in the Geneva Basin, and also to assess the depth of this type of activity. And we see that in the Geneva Basin, there are some situations that will be highlighted in the next few slides that could be actually to be considered very carefully. The inversion of focal mechanisms is important because it allows us to constrain the orientation of the three main stress tensors that are driving tectonic deformation in the area. We do know that faults that are more prone to be reactivated, they tend to strike about 30 degrees from the direction of sigma 1. In the Geneva Basin, we have strike-slip fault systems that are striking northwest-southeast. And this direction, unfortunately, if we consider the calculated direction of sigma 1, this direction is more or less west, northwest, east, southwest, along marked by this red line. And if we track the direction of this fault system, we see that these are actually falling right at 30 degrees to the direction of sigma 1. This tells us that all the faults that are actually being envisaged for geothermal prospection with a strike of 30 degrees to sigma 1 should actually be left alone. Geothermal prospection in Western Switzerland, to our opinion, should mainly focus on truss faults and faults that are less prone to be reactivated by the current tectonic regime. Since we have only 30 minutes, let me skip through these next three slides and go directly to another use of the seismic catalog that we acquired with this experiment. And try to harvest as much information as possible by a seismological experiment. In this work, to Maplanes, in the framework of Swiss National Science Foundation project, remove all the earthquakes that have been recorded by Veronica in the previous catalog and used only ambient noise to investigate and prospect for the velocity structure of the Geneva Basin. It is possible to use ambient noise that is everywhere present in our planet, to use it as a source to sample the velocity path across station pairs. In other words, we use the coherent signals that are produced by, that are characterizing ambient noise that is produced by ocean swells, anthropic noise, and any sort of, for instance, wind resonating across the cliffs of the mountains that is traveling from one station to another. Locally, this noise is scattered, but if we cross-correlate the signal that is passing from station A to station B, then we can retrieve a coherent signal that allows us to measure the properties that have been of the units that have been crossed by this coherent signal. So let's say that I have seismic noise traveling from station A to station B. I'm able to sample the trajectory and the physical properties of this segment between two stations. So with 3 stations, I'm able to measure 3 segments. And the more stations we have, the more segments we have to sample. And this is why seismologists always like to have several stations, because this provides a higher degrees and a higher resolution of our investigated area. It is also important to point out the directivity of the direction from which this noise is propagated. And in this case, for those that are not familiar with this type of chart, this is probably the best way to see at this chart is in decibels, so is like a power. N is the power of the noise and the direction of the noise that is coming in our is traveling across our network. In this case, we have a trajectory that is going from the northwest to the southeast, and some noise that is also more marked in the center of this network, that is the high frequency noise that is most likely related to the city of Geneva. So cars activity, urban activity, and so on. So why I'm discussing about the noise directivity? This is because the fault systems that are critical for our geothermal system are striking northwest southeast, and unfortunately these are almost perpendicular, almost parallel to the direction of motion of this noise. This means that the wavefronts will not be able to impact with the right angle these structures, and it will be very difficult to assess the occurrence of these structures with a noise directivity subparallel to the strike of the main fault systems. However, the direction and the elongation of the basin is almost perpendicular to the directivity of the noise, and this indeed allows us to have a very nice image of the shoulders of the basin and the entire basin structure. By analyzing this propagation of noise across our network, our seismometers are located here in white, it is possible to have what is so-called the group velocity maps. The group velocities are maps of the velocities of the surface waves, and they are proportional to the speed of the shear waves. So thanks to this representing these maps for different depths, is possible to reconstruct regions where there are lateral variation of group velocity maps, and then go, for instance, by considering only at periods of waves at the periods of 2 seconds, and then progressively going deeper, it's possible to sample different parts of our sedimentary basin. And in this case, we see that in the central part of the basin, for instance, there is a group wave anomaly where group wave velocities are slower. And in this case, as we know, that group wave velocities are proportional to the velocities of the shear waves, and the shear waves are extremely sensitive to the occurrence of fluids and of the occurrence of unconsolidated sediments, one could try to start to speculate about the occurrence of fluid in the central part of the basin. So the larger is the period, the deeper I can go with this exploration method. And this is for between 3 and 6 kilometers depth. So this allows us also to be able to reconstruct ISO velocities. And in this case, we associated the ISO velocity, a certain ISO velocity, to the occurrence of the basement. And therefore, it is also important because this method is important because it allows us to provide in 3D the depth of the basement without having to shoot active seismic and have to avoid complex logistic and costly acquisitions. However, I'd like to point out that this method is not always how to say this? It doesn't always hold one-to-one with the classical seismic refraction methods. In fact, here we reported the interpretation that is actually provided by classical reflection seismic, and where we see that the contrast of impedance of the methods that have been acquired with reflection seismic point out that the geological structures are actually tilted towards the alpine front. In the other case, we do not see for the active seismic, interpret from the interpretation of the active seismic, we do not see the structure of the sedimentary basin, that we instead are able to reconstruct with our acquisition. So there are most likely further research to be carried on to try to compare these two methods, and for sure these two type of information, the two type of information that are provided by these two different methods are holding complementary type of results. This is important because we map in 3D the morphology of the basin and the distribution of the shear waves in across the sedimentary basin. However, we are also dealing with fluids, because geothermal energy is about fluids, and we should start to locate the fluids in the subsurface. And in order to be able to assess what is the best area to investigate, we started to develop and to collaborate with colleagues from SINTEF and used MRST, the MATLAB Reservoir Simulation Toolbox. That is a MATLAB reservoir simulation toolbox that allows to compute Darcian flow in different geological contexts for different fluid flow scenarios, spanning from hydrocarbon, fluid flow simulation, CCS, and in this case, we started to develop also for large-scale groundwater flow. So we integrate all the information that we have seen in a mesh and start actually providing information about the petrophysical properties of each unit. Each lithostratigraphic unit has a sort of Gaussian distribution of the petrophysical parameters in 3D. So there is not only one value for each lithostratigraphic unit. And for the permeability, where we didn't have information about the variation of permeability with depth, we integrate where we had no data available, we integrated the formula of Manning and Ingebrigtsen for decay of permeability with depth. This allowed us to derive different temperature maps. And these temperature maps, they show at the surface, and this would not be a surprise for those of you that are familiar with fluid flow, these shallow fluid flow regions where fluids are mainly driven by the topography. So the topography plays a key effect on focusing and driving fluid flow. And the deeper we go, this topographic effect becomes less prominent. Just to give you a sort of information, here we have the Jura is in the northwest. So here we have the Jura chain. In the southern part, we have the Alpine chain, and the fluids are focused in the center of the basin, where higher temperatures are found. The deeper we go, I was saying, the less prominent is this topography effect present. In order to assess why it's important to take into account the morphology also of the surface, let me take this example, this cross-section that strikes from the Jura to the northwest to the Alps to the southeast. So the Jura is here and the Alps are here. Here is the time of the simulation, and as you can see, the cold fluids are mainly at the surface, hot fluids are at the base. We started from a typical geothermal gradient for the region, and with time we do see that the fluids are actually downwelling, driven by the hydraulic gradient below the topographic relief, and then they start to develop some broad and slow convection cells towards the center of the basin. This is very important because not only tells us where the fluids are driven and where they can be found, but thanks to the accurate petrophysical properties that were available for the Geneva basin, we are also able to say that in certain lithostratigraphic units, it would be possible to have very fast fluid flow regimes in the order of centimeters per year. We have some speed problems most likely in the upper part, but we also can say that in this case, these are actually fault systems. We can say that it would be possible to have even artesian, let's say, pressurized aquifers in the subsurface. We also had some control wells across the basin, and just to be very fair, not always these control wells are matching the final temperature. So this is the initial departing temperature of few wells, and this is the evolution over time throughout our simulations. It is important to point out that this is not always matching, but since we have only 3 control points across a sedimentary basin, the goal of the simulation is not to match the wells, but is actually to understand the physics of the process. Okay. let me continue with the final model. We have seen that we have a gravity-driven fluid flow towards the center of the sedimentary basin. And before, you remember, I called for a set of GPS coordinates. And now let's start to assume that you are the industrial company that actually started to have the concession for the exploitment of geothermal energy in Western Switzerland. And you have a set of sites that you want to select. Thanks to this set of sites, you select them based on availability, you can buy the land, or logistically accessibility of the site. And then you start to integrate our model, and you start to see that you shouldn't start to perturb certain fault systems, and then you can therefore start to remove, for instance, this site here that falls on a strike slip fault can be removed. Then you start to consider that you would take only the fault system, the sites that are falling nearby thrust fault systems, and then you can start to integrate another type of information. So the information coming from the geophysics, and information coming from the geophysics is telling you that there are some regions where group wave velocities might be slower, and in this case allows you to target regions where there is a higher chance of fluids to be found. And these are actually allow us to remove all a set of selected sites. And then thanks to this numerical simulation of fluid flow, we are able to select only 2 sites inside the basin, and therefore arriving to select only one site based on the fact whether we want to drill in the sedimentary cover and on the sedimentary basin. And this nicely corresponds to the location that we have been discussing at the beginning of the presentation. I have a few other more slides, and I was preparing for a 45-minute talk, so I would excuse myself if I have to cut down the presentation here. I think this is a nice wrapping point because allows me to tell you that we managed to develop over the last 5 years open softwares and open approach to investigate geothermal systems in an alternative way with an affordable approach, and to provide now with the next future experiment deeper and high resolution images of the subsurface to promote the development of geothermal energy in Switzerland and across the world. Thank you very much for your attention.
Thank you very much, Matteo, for this extremely engaging and interesting talk. I see already plenty of questions posted. I would envision more will arrive soon. So, Sebastian, please.
Yes, thank you very, very much, Matteo, for great talk, and always great to see your research and this really nice integrated research program that you have going on for yourself in Geneva. Yeah, Hadi said plenty of talks. I'm trying to group them a little bit.
Sebastian, I'm sorry first to check. Matteo, do you see us?
I see you. I don't see the questions, actually.
Okay,
yeah, but bring the questions up in a moment. So
yes.
We start with Wenlu, who says, thank you, very nice work. You referred to the seismic baseline before geothermal exploration. How will you work on the difference between triggered and induced seismic activities?
That's a very good question indeed. So induced seismicity, what do you mean by trigger and induced seismicity? There is always a bit of debate, and we should use carefully this terminology. Induced activity is when we start to stimulate, and trigger activity is when you have a passing seismic waves released by, for instance, another earthquake and promote some seismic activity in a system that is already in a critical state. So for sake of the discussion, and to address this question, I will discuss only about induced activity and natural activity, leaving on the side the trigger activity promoted by regional earthquakes. So we know that now we have a network that has a magnitude of completeness down to, I think, 0.5. So this is super accurate and is almost as good as it can be done for a sedimentary basin of this kind. So anything that would increase remarkably the seismic activity would have to be ascribed to induced seismicity, whether if we are doing, if in Geneva they were to develop EGS, for instance. But for the moment, this is not the case, because geothermal energy in western Switzerland is mainly for hydrothermal purposes. So hydrothermal energies is normally not related to seismic activity, unless there are bad chance something like a pocket of gas is found, so this would create a kick in the well, as already happened in eastern Switzerland. But anything that would actually relate to seismic activity far away from the well would be regional activity, and anything close to the well would be induced activity. I'm not sure if I addressed your question, though.
Van can always comment if he has more questions. He actually has a few more questions. I'm going to take some other questions first. So let me see. So Mengji Zhao says, thank you for the interesting talk. What conditions would be needed to be considered for proper site selection when we know we should also manage heat and be able to store it nearby? It's a follow-up comment. Should the geothermal site be constrained also with this best storage of heat location? In Geneva, you're trying to do both storage and production.
Yes, if you want, I must admit that our approach is a purely academic approach, and on the at the interface between geophysics and fluid flow, basically. Actually, there is also another set of points that have to be considered that are purely engineering problems, like how do you store it, which part of the city requires more heat, which part of the city requires more electricity. In this case, there are our colleagues from environmental sciences that are carrying on how to distribute the energy and run simulations on what are the districts of the town or the city that would require more geothermal heat or geothermal energy. This is outside my know-how, but there is a close collaboration with colleagues from the environmental department that are simulating this aspect. And as I said, very often the selection of few sites starts from looking at simply the logistics around, whether you can buy the land, where you can find nice people that would sell you the land for free, you can bring current easily, access to roads.
Thank you. Yeah, and I think there's a really interesting question, actually. How do we live in the cities of the future? How do you supply them with energy, which we don't know how much energy we need in future cities. So there are lots of variables to consider. But if you don't get the geosciences right in the first instance, then everything else sort of may not work as you wanted to. We have a question from somewhat ominously called Mr. JVIJ. I don't know who that is. Maybe Hardy knows. It says, thank you for the great talk. You mentioned active geophysics to characterize the reservoir. Can you derive in situ temperatures with these methods? If so, how? With electrical, also with seismic methods?
Wow, this is a question I'm not sure how would I address it. So I mentioned active geophysics to characterize reservoir. Yes, because when we work at the large scale, our approach is to minimize cost, to narrow down the region where you would do the actual real prospection with the sound methods that are commonly used by the industry sector. So you can imagine that a 3D active seismic campaign has a certain cost, and maybe you don't want to spread it all across your basin. You just want to focus it. With the approach I presented here, we would be able actually to narrow down and say to the industry, okay, maybe instead of doing like a 3D seismic campaign 15 kilometers by 15 kilometers, you can simply focus on a 2 by 2 kilometers and invest there. Then how to measure the temperature with geophysical methods in the subsurface. To the best of my knowledge, I'm not aware about any geophysical method that on the surface would be able to measure the temperature in the subsurface, unless you have a prospection well in the region and you do some interpolation with the classical Petrel or approach.
Taking a question from Marty Bone, who has quite often helped to with chairing the webinars when Hardy was busy. So Marty asked, thank you for the nice talk. Can you please comment on the role of thermal stress along with the mechanical stress have you also studied the impact of thermal stresses and specifically plastic deformation in the rocks over time?
No, I haven't studied the plastic role, also because we are dealing with the upper crust and we assume that we only have ductile deformation. We rather tend to focus on the role of fluids that then can actually shift, the location of sigma 2 and maybe promote a normal fault into a strike slip fault. In terms of plastic deformation and this type of rheology, this could be maybe for the deeper parts of the Alps, but is mainly more something that is addressed by my metamorphic colleagues, for instance, the University of Lausanne. So we only focus with the brittle deformation.
Thanks, Matteo. The two very related questions. So I'm going to read them out both to you. We're getting something to the mitigating seismic risks. The first one is again by someone who has helped with chairing the webinar in the past, Maren Bremer. Dear Maren, thanks a lot for this interesting talk. After the experience in Switzerland with induced earthquakes, would you still recommend to target faults or better avoid them and drill for dense fracture zones? And someone you've worked with in the past, Eric Singer, says hello and asks, major seismic events due to geothermal projects are due to the reactivation of faults. When you want to find the best place to drill, you still focus on fault systems, or were there alternatives in the Geneva area? So faults versus fracture zones, are faults the best place in the Geneva area, considering problems that Switzerland had with seismicity?
Okay, so how to say this? I am a earth scientist, and my know-how is where to find sites that could be easily, that could have higher chances of holding fluids. So to do so, we developed these group velocity maps. Group velocity maps are sensitive to shear waves, and shear waves are sensitive to fluids. We have a distribution of the area, then it's not me who decides whether to actually drill into fault systems or in fracture zone. As I show you at the very beginning, the target and the strategy of the canton is indeed to target fault zones. Where do I have it? This is here. So these are the 4 wells that are being planned and proposed and approved to be drilled in the Geneva Basin. So my first concern was to see, we have a truss system, we have a strike slip system, shall we leave any of those alone? Then the answer that we provided in this specific case scenario is yes, we should leave definitely strike slip fault systems alone in Western Switzerland, and I would say also in Switzerland in general. Fracture zone, I think, is actually a better target. Based on our group wave velocities, we do see anomalies in the center of the basins. And now, sorry if I'm switching back and forth, but I just need to point them out. So you see that in the basin, the center of the basin, there is this large attenuation where there are very little faults, but the sedimentary cover is thicker. In that region, there is actually the Lias is fairly well reachable. And if we want to do a St. Gallen type of experiments, where we have either thermal, geothermal energy, I think this would be actually a better site. And also to, start to build confidence with the population about induced seismicity and the problems associated to faults and seismic activity, I think it could not be a bad idea to target fractured reservoirs instead of faults. Having said so, I am an academic working at the university, and I can give my opinion, but then it's not up to me to decide.
You're not the regulator. The regulator at the end needs to make the decision to provide evidence. Thanks, Matteo. So we have a couple of questions from Anna Kotsova. It says, thank you for your talk. Could you tell what is the best parameter to monitor dynamically in the doublets, and what would be the mitigation strategies once microseismicity starts to be observed? Continues, would it be always the best to stop production injection? Can we do better to keep the production of heat going while mitigating the start of seismicity? So how do we monitor, detect seismicity, and what do we do once things start rumbling?
So there is actually a traffic light system that is envisaged for all the geothermal systems that are being developed in Switzerland. There is the way this is structured nowadays is that there are private companies that can monitor these systems, and during well there is the SED, the Swiss Seismological Service, that has the supervision of these deployments. So when there are certain parameters that are part of this traffic light system that are becoming, saying a message no-go, the system is stopped, and most likely, if you are in the case of an enhanced geothermal system, we don't have this case yet in Switzerland. You would close the system and let it eventually diffuse and pressure to diffuse. But as I say, this is far away ahead of time, and it's not being developed at the moment. In terms of mitigation, is always a good. We take a chance, but it's important, I think, in terms of communication, to mention that there are different types of geothermal energy, and not all the geothermal energy is associated with earthquakes. There are geothermal energy that basically brings very little seismicity, as you don't stimulate the reservoir.
Thanks, Matteo. When Lou asked the first question, he also had a second question is related to sort of the discussion we just started. That he asked, how would you avoid the noise from fluid flow in the wellbore, if possible, without shutting down the well? So what if you have downhole geophones? He clarifies later on that by avoiding mitigating or trying to increase the signal to noise ratio.
I wouldn't know. I am not an expert on reducing the noise during fluid flow during the monitoring. As I said, we are working mainly at the large scale and not at the fine scale. So these are methods used by other teams, and I wouldn't be able to address this question.
Thanks, Matteo. No questions coming through at the moment, so I can ask you a question, which I haven't done for a long time. I mean, you're doing essentially the geothermal exploration, trying to select sites that are possible hosts for developing geothermal energy. In terms of the tools, is there anything that is absolutely needed, or are all the tools now in place, emphasized on the open source type nature, to do this routinely with the appropriate care? Because you think of the oil and gas industry, how much they spend on seismic surveys and specialized softwares in lots of detail. So what are your views on the missing technology, missing tools?
I think, Sebastian, you nailed the problem, because one of the problems of geothermal energy is that very often we don't have in the sector the financial means of other sectors. So this means that it's not possible to buy expensive software, it's not possible to do 3D seismic everywhere. And I think the industry here has a role that is central, and let me stress central, because they need to believe that there are alternative methods that can be used. So I can develop ambient noise as much as I want, I can include resolution, but if there are no companies that start to believe that this is possible, that we provide reliable informations, then it becomes critical. And as you know, the geothermal sector is a new sector. To the best of my knowledge, just until 10 years ago, there were no specific master program on geothermal energy. So most of the people are migrating from other domains. And other domains are characterized by other means. So we have to make a new mindset and start to promote the new method that are available, because otherwise, we are stuck with expensive methods, we are stuck with software to buy, we are stuck with 3D active seismic that is held in a much better degree of confidence compared to what I present today, but we would not be able to launch a thermal project. So this, I think, what is missing, that we trust each other and we go hand by hand forward.
I think isn't the development in Munich, where they did an extensive 3D seismic survey and that helped them to de-risk some of the exploration, isn't that sort of like a good example how technology and how the proper tools, the proper data can really help you to do this? Costs, yes, as a community, as a city, it costs you additional money, but it helps you to de-risk your project so much that at the end of the day, it's much more worth it than drilling a dry well or causing whatever problems. Basel is almost the worst case scenario that you lose.
If I could interrupt, I guess you have had a lot of time asking him many questions, so let us also have a chance of interacting with him and asking his opinion on some also somehow, Matteo, on conflicting matters. Swiss society has observed problems with geothermal as well, and the public perception also somehow matters in the research that we do, etc. Do you see a specific thing that is still in the universities we are supposed to develop in order to make it more accepted by the society, or do you see any type of resistance by the policymakers to scale it up faster than you would expect them to do?
I think there is a lot of work that should go in communication. Very often we are focusing writing papers, publish, and we don't take the time enough to, transmit our know-how. We have seen in Switzerland there was a referendum about geothermal energy, and in Canton of Geneva, where I am at the moment, they invested very much on communication. They organized open days, they organized the Industrial Service of Geneva did an excellent job in taking the time to talk to the people and explain that not everything is Basel, not everything is about induced seismicity. There is another geothermal energy, and I think this is another important gap that can be bridged.
So what's the plan of now the government for scaling up geothermal energy in Switzerland?
So there is an excellent program supported by the Confederation where they provide, I think, is up to 60% funds to develop geothermal systems, and they back you up if your wells are dry. So there is some sort of insurance. As a trade-off, they have to provide, each of these projects needs to provide an innovative component. So us to bring something to the market with new methods that should be introduced in this framework. And this is what we are doing, for instance, with other geothermal projects here in Switzerland. We are the academic counterpart that we develop the method, we try to introduce and push forward the exploration.
I see. So that would involve a lot of universities also, like Geneva, to also get involved with this scaling up project in the nation as well. That's quite a good opportunity, actually, to train next generation of geoscientists.
I think it's an excellent opportunity for the students because they are exposed to real problems of the industry. Not everyone wants to undergo an academic career, and they're exposed, in our daily discussion, in our present. When you teach in a master class, you prepare your slides and you talk about the problem you had a month ago, and this percolates to the students. And I think this try to interaction between the academia, the industry, is something that has to be fostered further, but is there and should be nourished.
But thanks a lot. So we conclude opening up the science to the society, speaking in their language, making sure there are other aspects. There are risks to all technologies, but also opportunities to get into. These are the things that we learned from your comments, and thanks a lot, Matteo, for sharing this fantastic experience that is Swiss also government is growing up, is scaling up the geothermal, and especially including universities and the society in it. It's very encouraging.
Thank you for hosting me today.
No, you're most welcome. I think there are no further questions from the audience, and time is reaching the full hour. So normally I would say, Hadi, over to you, but you already started the closing remarks, Hadi.
I thought that
Hadi,
give me time to ask.
Hadi, so Matteo, thank you very much again for the great talk. Thank you to the audience for the excellent questions.
Yes.
And Hadi, now over to you.
Thanks very much, Sebastian and Matteo. So I would like to take the chance to introduce our next week's speaker. Next week we will host Phil Warden from TU Delft. Phil is my colleague in the same department, Geoscience and Engineering. He leads the geothermal research program here in TU Delft. He will speak about geothermal pilot cases, developing an urban energy laboratory. Until next week, it will be 11th of November. Stay happy, healthy, and tuned into this channel, 4 p.m. Central European, 3 p.m. British time, and 7 a.m. California, for another geoscientific and geoenergetic talk. Thanks a lot, Matteo, and enjoy your time, and especially weekend that is upcoming as well.
Thank you very much.
Thank you, everyone.
Thank you.
Bye-bye.
Bye, everyone.
Bye.
Bye.